and I will talk about the sequential design algorithm that Eric was talking about before, which is called MICE. And this is a work that was done together with Serge when I was at UCL. And first I will just talk about Gaussian process emulation. After that I will talk about this algorithm that is called MICE, which is a sequential design algorithm for computer experiments. And after that, demonstrate it for some test functions and a tsunami model. So, okay, so what is a computer experiment? It literally, in our setting, would be that you have some deterministic computer simulator with a real valued output. So we assume that it is just a scalar. So we denote that by y, and that one depends on some inputs x, that is a vector with the p arguments. So this one, for instance, would be, let's say, model parameters, and you want to be able to run this model over that design space called capital X. The purpose of this work is that if these models are very expensive, you might not want to do, let's say, a large number of runs of it to be able to compute, let's say, expectations and so forth. So what we want is to be able to say that we want to do n runs, but we're going to do it on an approximation of that model output that is built on some small n that is much smaller than the capital M. So this is the point. And we want to be able to make predictions in this design space for inputs or model choices that have not been run before. So the training data is denoted by D, and that one consists of a matrix X that would then be, each row then would be one of the design points. The corresponding Y's would be the outputs, which was scalar. And we want to be able to create an emulator based on some small n of the simulators. So we're going to treat that the output y is actually a Gaussian process, which means that our set y would then be a multivariate normal distribution. And this is just the standard mean expression for this Gaussian, and this would be the predictive variance. So the predictive variance is given by x squared. And the correlation matrix is denoted by k. So this would be a typical figure of Gaussian process emulators. On the left, you have the one-dimensional case. So the vertical axis here would be the output, and the horizontal would be the input parameter x. And on the right-hand side, it is the shape of the function built in a two-dimensional domain where you have x1 and x2 as your inputs. So this would be the approximation built over the blue dots, which would then be design points. So this talk is about the sequential design, and the sequential design would allow that you also can do an adaptive way of collecting which design points to run your model. And also it is cheaper than if you would try to identify what is the best design before you have actually evaluated your model. But the price would be that you have something that is suboptimal. Okay, so the sequential design algorithm would be the following, which is just that you're trying to find the argument for the maximum of some objective function f. So this f is changing as you go, so in each iteration k, you are going forward and then you're changing your design criteria because you learn something about what would be the best point that you want to choose. Some notations here would be that D0 would be the initial design. And then you would say here the X-cand here would be the candidates in this design space that you're allowed to evaluate your simulator that you can pick from. And you want to pick the best one in each iteration from that set. And this XG is a discretization grid over your design space, which would be basically a discretized version of your design space. So we moved away from a continuous design space to something that is discrete. The most common ways of designing in terms of sequential designs for computer experiments would be the active learning McKay, which is denoted by ALM. And that is basically that you're just maximizing the predictive variance of this Gaussian process emulator. And then you're choosing from this candidate set the one that had the highest variance. The benefit is that this is very fast to do. The negative would be that when you, for instance, would have many points in each direction, then the number of boundary points will grow with the order of or exponential to p, which means that in a 4-dimensional space with an equidistant grid of 10 points in each direction, 60% of your points would be on the boundaries. So this is a kind of a negative drawback because this one would pick the maximum variance that typically would be on the actual boundaries of your domain. So if most of your points are on the outside of the domain, you will not really explore the interior. So the active learning cone is similar, it's just that you are instead maximizing the integrated variance over the design space, where you're choosing to add this extra candidate point, and then you take the difference with if you had it or if you didn't have it, and then you integrate it. So this is more expensive because you actually have to do an integration over your design space. So just to have one figure of how the predictive variance would look like in 2 dimensions is that you can see here that the red would then indicate a large variance, and you can see that it typically would be on the boundaries because of the problem with the extrapolation. Whereas the integrated variance, or the ALC, is more complex to know where to add the next point in this space, because you have to understand the effect that that extra point would have on your domain. So the algorithm I will talk about today is based on what's known as mutual information. So it's the difference between what's known as information entropy, between some random variable and the entropy if you have that random variable conditioned on another. So it basically is the shared information between 2 random variables that we denote here by Z and Z prime. This mutual information criteria that was proposed by Andreas Krause was that you should look at the mutual information between basically the Gaussian process that you have on your current design set against the Gaussian process for the remaining part of your space. So it's basically 2 random variables, and you want to be able to say that the design that I have, or the Gaussian process that I built on my design, should tell me a lot about basically the remaining part of the space. So this is the derivation that they did, which is that you do it in a greedy way, where you're just looking at the mutual information with this extra point and without. And then you're doing some calculations with entropies, and you're exploiting that you have a Gaussian process, which means that you know that you have an explicit form of these 2 entropies. And then you take the difference of those 2, and then you will get a ratio between 2 predictive variances. One that is built on your current design set that I denote here by K, and then you, in the denominator you would have basically your G, which is all the points in your discretization of your space, subtracting the design point you already have and your candidate point. So this ratio is the design criteria, which is known as mutual information. So this is the problem he looked at, and he looked at something that had an equidistant grid, and you want to choose the optimal sensor placement. And they also did derivations where they showed that this is near optimal. So doing this sequential greedy approach, you are basically not far away from if you would have done it in one batch. Okay. So this is the near optimality result that they shown for an equidistant grid. So basically the mutual information for a certain design, IN, is bounded by the optimum and runs 0.67 times the optimum. And that is if you would do the sequential instead of doing the direct approach. But the direct approach you can't always do because you have to fit correlation parameters in your covariance and these hyperparameters, which means that the sequential design might even be necessary to be able to capture the covariance. A practical issue with the algorithm is that if you look at the left side, we have the two-dimensional design space, and these are the candidate points. So here you can see the criteria values marked in the colors, and everything seems fine. And the black dots are the current initial design. On the right-hand side, I added an extra point close to one of the other points, and you can see that it would basically choose one of those 2 points. So it means that it's not stable to if you don't have a particular structure of your design. So we were thinking, okay, we want to use the mutual information in high dimensions. So then you can't use an equidistant grid that keeping all the points separated. So we had to come up with a way to avoid that something like this would happen. Because the proof of the method or the algorithm itself was based on that you have something that is equidistant. So what we did is that we extended what they have been doing to both do adaptivity in finding your hyperparameters, but we also introduced a nugget parameter to the diagonal of your covariance. So, but we only do it on the denominator, which was the reason for which you get this really high value of your mutual information, because the variance is close to 0 if you have a candidate point close to a point that already exists. So how does that look like? So if you do that, adding this nugget parameter, and we just try some different values of the nugget parameter, the black would be that you don't add it. Basically, it's a very small value. So you can see that this predictive variance is close to 0. And that means that you would be able to get very high values. But if we're adding the nugget that is around 1, you kind of get a similar shape, but and it stays away from 0. But an interesting thing is that if I would have chosen 10, it basically becomes flat. And the reason is that if you're looking at, which would be in the paper, is that you can look at what is the variance on the points that are part of your design. And you can actually see that as soon as the nugget parameter is larger than 1, you get a growth in variance on the design points. So 1 was the one that keeps the shape basically without actually having that issue. And then we perform that for many cases. This is to illustrate the point, which is that you see here on the bottom, you see a left design and the right design is 2 Latin hypercubes. And you basically can see that you have kind of similar kind of criteria values across the design. And on the top, this issue that you have 2 points close to each other actually doesn't matter anymore. So you would choose the design that the original mutual information would have chosen. So you are removing that issue. This is a visualization of some example of what have been done. Like say if you do ALM, you see that choosing the boundary points, mutual information choosing more in the interior, and the ALC is also choosing more in the interior. So this one have a bit more similar kind of behavior as the ALC, but I will explain why this criteria is computationally more attractive. So the comparison in terms of the computational cost is that the ALM is growing with the design capital N, the number of design points, in square, whereas the ALC and MICE is cubic. So the only issue is that with ALC, you have this extra multiplied by nref, which would be the number of integration points that you needed to compute your expectation. And that is what is making the ALC, if you're looking in the bottom figure on running times, you will see that the ALC's growth of running time grows extremely fast because you have that extra cost. Whereas the MICE, for instance, on the right, you can see that it has a much lower cost. Something to point out is that, it might be hard to see here on the screen, is that the lower bars are basically the fitting of the maximum likelihood. So most of the cost is actually maximum likelihood. But in the implementation now here at Alan Turing, they have a more efficient implementation of this. So this cost is going to be much smaller. But the point is the red part that is crossed, which is the algorithm cost of selecting. And you can see that the integrated variance is very expensive. I will show you some test examples. So this is the oscillatory function. So in the horizontal, you have the number of design points, root mean square predicted error on the vertical. And you can see, I can just point out that the crosses and so on is basically the maxi-min Latin hypercubes or minimax Latin hypercubes. The cyan-colored one is the mice without using the nugget. So if you just will use the standard mutual information. And you can see that it's almost doing as bad as the Latin hypercubes. But then if you would choose this nugget to 1, this regularization of the denominator of your criteria, you can see that it's doing exactly the same as the ALM and ALC. And then for an 8-dimensional problem, we also have a comparison, and then the red here would be mice. And you can see that it's doing better than the integrated variance, which is the ALC or the ALM. And this 7-dimensional problem, we have the similar kind of thing, where where basically these extra numbers you see on each method is basically the number of candidate points that I allow them to have. And the ALC can't afford too many because of this integration, so it's 150. But I also compared the mice with 150 to have a comparable performance. Okay. We have a tsunami modeling example, which is basically 4 design parameters. You have this landslide that moves down in the water, propagating a wave, and on the other side of the coast, you're measuring the run-up wave, basically the height, the maximum elevation. So you have the spread, which is one of the parameters that are changing, the height, basically the depth of the sea, and then we also have the angles of this domain. Each run takes about 15 minutes, and then we did a comparison here. Number of design points against the error. MICE is doing better than both the other methods, and I also added the confidence bands of these runs. On the right-hand side is the actual run time against the error. So you can see that it's also doing better. And you can even see that the ALC, the blue one, is actually doing not better than the ALM. Because the ALM have, in terms of algorithm, is very cheap. So if you actually compare the runtime instead of design points, the ALC will have a disadvantage when you're going up to more design points. And so this is so this is the explanation of why MICE is doing very well and are competing with this previous classical ALM and ALC, and it does have a better work complexity. There's also an extension on this where you're using MICE in optimization. And I'm just going to talk briefly about it, but basically it is one of these upper confidence band optimization routines. And it is using either MICE or ALM, and it's using it for the actual exploration. So it's doing it in batches where some of it is used for exploration and some of it is used for exploitation, which is more the direct to choose the optimum. And you can see here that the red is the MICE is doing better than if you're using ALM. It's also doing better than the efficient global optimization, which is a very popular criteria. And then on the right-hand side, it is I think it's a 4-dimensional problem. This is a 2-dimensional, and then it's also doing much better than the 2 other methods. This work is not my work, so it's just basically because it is a work that is using the MICE algorithm and showing that you can use it in various settings. And it is this upcoming paper, surrogate-based optimization using mutual information for computer experiments. And these are some references. This is the reference to this work. This is the reference to the mutual information that was used for sensor placements. This paper here, emulation of higher order tensors in manifold Monte Carlo methods for Bayesian inversion problems. They use this method to be able to do proposals in MCMC. And then the one I just mentioned, optimization one, And this is just a reference to the tsunami model that now have been further extended, and we're going to do some work with mice in that setting for more realistic cases. Thank you.